You think you understand electricity, you use it every day. You charge your phone, you turn on lights, you start your car. Electricity is everywhere. It powers your life. It's as common as water. So you must understand it, right? Explain it to me. What is electric charge? Not what does it do? What is it? Where does it come from? Why does it exist? You'll probably say something about electrons. Electrons have charge. Okay, but that's not an answer. That's just naming the thing that has the property. I asked what the property is. Try again. Why do electrons have charge? Why is there such a thing as charge at all? Now you're stuck. And here's the thing that should bother you. So is everyone else. Every physicist, every engineer, every Nobel laureate who ever lived. When it comes to the deepest question about electricity, the question of what charge actually is, we hit a wall. We don't know. And that's not a failure of science. That's science being honest about its own limits. The universe doesn't owe us explanations that go all the way down. At some point, you hit bedrock. You hit the place where the only honest answer is that's what we measure. That's what the universe does. Electric charge is one of those bedrocks. But let me show you how strange that bedrock really is. Let me show you what we do know and why the things we know should absolutely astonish you. Start with the most basic fact. There are two kinds of electric charge. We call them positive and negative. That's it. Two. Not three, not seven, not a continuous spectrum. Exactly two. Why two? Why not one? Why not five? Nobody knows. It's just a fact about the universe. We observe it, we measure it, we use it. But we can't explain why the universe chose two kinds of charge instead of some other number. Now here's the rule those charges follow. Like charges repel, opposite charges attract. Positive pushes away from positive, negative pushes away from negative. But positive and negative pull toward each other. Again, why? Why this rule and not some other rule? Why don't like charges attract? Why don't opposite charges repel? We don't know. This is another piece of bedrock. The universe just works this way. But watch what happens when you combine these simple facts. Two kinds of charge, like repels like. Opposites attract. From these simple rules, from this minimal starting point, you get everything: chemistry, biology, the solidity of matter, the light from stars, your brain working right now. All of it traces back to these rules about charge. That's not an exaggeration. Let me show you. Pick up any object, a pencil, a coffee mug, your phone, hold it in your hand. What do you feel? You feel solidity, resistance. The object pushes back against your fingers. You think you're touching it. You think the atoms in your hand are making contact with the atoms in the object. Wrong. The atoms never touch, not even close. What you're feeling is electromagnetic repulsion. The electrons in your hand are pushing against the electrons in the object, and electrons repel each other because they have the same charge. Negative repels negative. That repulsion is enormous, incomprehensibly enormous. The electromagnetic force between two electrons is about 10 to the 42nd power, times stronger than the gravitational force between them. That's a 1 followed by 42 zeros. Gravity, the force that holds galaxies together, the force that keeps planets in orbit, is laughably weak compared to electromagnetism. So why doesn't everything explode? If these forces are that strong, why isn't matter tearing itself apart right now? Because of cancellation, atoms have both positive and negative charges. Protons in the nucleus are positive. Electrons orbiting around are negative. In normal matter, the positive and negative charges are mixed together, intimately balanced. Every push is countered by a pull. Every repulsion is countered by an attraction. The enormous forces are still there. They're acting right now in every atom of your body. But they're balanced so precisely that the net effect is nearly zero. And because the forces are so huge, even a tiny imbalance creates effects you can feel. Rub a balloon on your hair. You've transferred maybe 1 electron in every trillion from your hair to the balloon. That's essentially nothing. But now the balloon sticks to the wall. Now your hair stands up. Because when the underlying forces are that enormous, even the smallest asymmetry produces visible results. This is the secret hiding behind ordinary matter. Everything you touch, everything you see, everything you think of as solid and stable is actually a carefully balanced war of titanic forces. Electrons screaming away from each other, protons pulling electrons in, the whole system held in a precarious equilibrium. That equilibrium is you. That equilibrium is the chair you're sitting on. That equilibrium is the planet under your feet. Now let's go deeper. Let's ask how these forces work. You push your hand down on a table. the table pushes back. That seems normal. That seems like contact. But we just established that the atoms never touch. So how does the table know your hand is there? How does it push back at exactly the right strength? The answer is fields, electric fields. Every charged particle creates a field around itself. The field extends outward in all directions, filling space. And when another charged particle enters that field, it feels a force. The force is the field acting on the charge. This is how electromagnetic forces work. Charges create fields. Fields act on charges. The field is the middleman, the messenger, the thing that carries the force through space. But here's where it gets strange. What is the field? Is it a thing? Is it made of something? Or is it just a mathematical convenience, a way of describing action at a distance? Physicists have argued about this for centuries. And the honest answer is, we're still not sure. The field is certainly useful. It lets us calculate. It lets us predict. But whether the field is a real physical entity or just a description, that question doesn't have a clean answer. What we do know is this. The field contains energy, real energy. The field can do work. The field can push things around. In that sense, the field is as real as anything else. It's not nothing. It has physical consequences. And here's the really strange part. The energy in the electric field around a charged particle extends to infinity. Every electron, every proton has a field that reaches out forever, getting weaker with distance, but never quite reaching zero. The field fills all of space. It touches every corner of the universe. When you wave your hand, you disturb the electromagnetic field. That disturbance ripples outward at the speed of light. In principle, that ripple eventually reaches the most distant galaxy. You've made a change that propagates across the entire observable universe. That's not poetry, that's physics. The field is everywhere. Now let's talk about something that should break your brain. We said like charges repel. Negative pushes away from negative. That's why your hand can't pass through the table. Electrons in your hand, electrons in the table, both negative, they repel. But wait, your hand is full of electrons. Your hand is full of negative charges. Why don't the electrons in your own hand repel each other and blow your hand apart? They're trying to. They're pushing away from each other right now. But they're stuck. They're trapped in atoms held in place by the positive charges of the protons in the nuclei. The attraction to the nucleus is stronger than the repulsion from other electrons. So the electrons stay put. But think about what this means. Every atom in your body is under stress. Every electron is pushing against every other electron. Every atom is a system of forces and tension. You are being held together by attraction that's slightly stronger than the repulsion that's trying to tear you apart. If you could somehow remove all the positive charges, if you could strip away the protons, the electrons would explode outward with unimaginable violence. The repulsion would be unopposed. The forces that are normally balanced would suddenly have nothing to fight against. This isn't hypothetical. This is what happens in certain kinds of explosions. Not the chemical kind, not the nuclear kind, the electromagnetic kind. When you build up enough charge in one place, enough imbalance, the forces become irresistible. Lightning is this, a spark is this. The buildup of charge creates such enormous repulsion that the air itself is torn apart. Electrons rip from atoms, a channel of conducting plasma created in an instant. Lightning is just electrons desperately trying to get away from each other. The flash, the thunder, the violence of it, that's electromagnetic repulsion expressing itself across miles of atmosphere. Now let's talk about something that puzzled physicists for a long time. How fast does the electric force work? When you move a charge, the field changes. Other charges feel the new configuration. But how quickly? Is the effect instantaneous? Does the force travel at infinite speed? No. The effect travels at the speed of light. When you move a charge here, a charge over there doesn't feel the change until enough time has passed for light to travel the distance between them. This was one of the great discoveries of the 19th century. Electromagnetic effects propagate at the speed of light. And that discovery led to an even bigger revelation. Light itself is an electromagnetic phenomenon. Think about that. Light, the stuff you see with, the stuff that lets you read these words, is a ripple in the electromagnetic field. It's a disturbance traveling through space, a wave of electric and magnetic fields oscillating together. When you turn on a lamp, you're making the electromagnetic field vibrate. Those vibrations travel outward, enter your eyes, trigger the electrons in your retina, and you see. Vision is electromagnetic interaction. So is radio. So are X-rays. So are microwaves. All the different kinds of electromagnetic radiation, from radio waves to gamma rays, are the same phenomenon at different frequencies. They're all ripples in the field that charged particles create. The field connects everything. Charges here, changes there. Vibrations propagating at light speed. The entire universe is woven together by this invisible web of electric and magnetic influence. Now I want to show you something that goes even deeper, something that should disturb you in a good way. We've been talking about electrons as if they're little balls, tiny spheres with negative charge attached to them. That's the picture most people have. That's the picture that's useful for everyday calculations. But it's not quite right. When physicists tried to take this picture seriously, when they tried to calculate the properties of a tiny charged sphere, they ran into problems, serious problems. If the electron is a ball, how big is it? What's it made of? Why doesn't the charge on one side of the ball repel the charge on the other side? These questions don't have good answers. The classical picture of the electron as a little ball leads to contradictions. The energy stored in the electric field of a point charge turns out to be infinite. The self-repulsion of the electron should make it explode. The whole thing doesn't quite make sense. Eventually, physicists developed quantum mechanics and later quantum electrodynamics, and these theories handle electrons in a completely different way. Electrons aren't really little balls at all. They're more like excitations in a field, patterns in the quantum electromagnetic field, localized disturbances that behave in certain ways. But even quantum electrodynamics doesn't answer the question of what charge is. It gives us incredibly precise predictions. It tells us how charges interact to 11 decimal places. But it doesn't explain why charge exists or why it has the properties it does. The mystery remains. At the deepest level, we don't know what electric charge is. We just know what it does. And that's okay. That's actually the honest state of physics. We're not in the business of explaining everything down to the bottom. We're in the business of describing patterns, testing predictions, finding regularities in nature. When we hit a regularity that can't be reduced to something simpler, we call it fundamental. Charge is fundamental. We accept it. We build on top of it. But let me show you something beautiful that we have figured out, something that connects all of this together. Electricity and magnetism are not separate phenomena. They're the same thing seen from different perspectives. Move a charge, and you create a magnetic field. Change a magnetic field, and you create an electric field. They're intertwined. They're two aspects of one unified force, the electromagnetic force. This unification was one of the great triumphs of 19th century physics. Maxwell figured it out. He wrote down 4 equations, 4 compact expressions that describe all electromagnetic phenomena. Everything from static electricity to light to radio waves to the force holding atoms together. All of it follows from Maxwell's equations. And those equations reveal something startling. If you wiggle a charge back and forth, you create a self-sustaining wave. The changing electric field creates a changing magnetic field. The changing magnetic field creates a changing electric field. Back and forth feeding each other, the disturbance propagates outward at a specific speed. Maxwell calculated that speed. It was the speed of light. That's how we know light is electromagnetic. Maxwell's equations predict it. Wiggle charges and you make light. And indeed, that's exactly what happens in a light bulb, in a star, in every source of light you've ever seen. Charges accelerate, fields oscillate, and electromagnetic waves radiate outward. The light from the sun is 8 minutes old when it reaches you. It's been traveling through empty space at exactly the speed Maxwell's equations predict. Charges on the sun wiggling, fields propagating across 93 million miles, hitting your skin, warming you. Electromagnetic force reaching across the solar system. This is what you're part of. This is what you're made of. Your atoms are held together by electromagnetic force. Your nerves fire through electromagnetic interactions. Your eyes detect electromagnetic radiation. Every sensation you've ever felt, every thought you've ever had, runs on electromagnetism. And here's the thing that brings us back to the beginning. Despite all this understanding, despite Maxwell's equations and quantum electrodynamics and precision measurements, We still don't know what charge is. We know the rules it follows. We know the field it creates. We know how it interacts with other charges and with light. We can predict, we can calculate, we can build technology that manipulates charge with extraordinary precision. But why charge? Why this property? Why does matter come in two varieties that attract and repel? Why does the universe have this particular feature? We don't know. And that's not because we haven't looked hard enough. That's because some questions might not have answers of the kind we're looking for. Some things are fundamental. They don't reduce to something simpler. They're the starting point, not the ending point. If you find that unsatisfying, I understand. Humans want stories. We want cause and effect chains that lead back to some ultimate cause, some final explanation. But the universe doesn't owe us that. The universe is what it is. Our job is to describe it accurately, not to force it into the shape we find comfortable. What we've discovered about charge is extraordinary. Two kinds. Like repels, opposite attracts. The force falls off with the square of distance. Fields mediate the interaction. Light is electromagnetic waves. Electricity and magnetism are unified. Matter is held together by balanced repulsion and attraction. That's a lot. That's enough to build computers, to light cities, to understand how stars work, to explain why you can't walk through walls. That's an enormous achievement. The fact that we can't go deeper, the fact that we can't explain charge itself, isn't a failure. It's a recognition that we've found the floor. We've found the place where explanation stops and description is all that's possible. And honestly, that should inspire awe, not frustration. We live in a universe that has fundamental rules, rules that don't come from anywhere, that aren't made of anything simpler, that just are. And one of those rules is charge. You're made of it. You run on it. You experience the world through it. Every push, every pull, every light, every color, every thought. Electromagnetic, that's the secret of electric charge. Not that we've figured it all out, but that we've figured out enough to know where the mystery really lies. We've pushed through the superficial explanations, the labels that rename without explaining. We've reached the actual bedrock. And at that bedrock, we find something we can describe perfectly, but explain not at all. A property of matter that makes everything work. A force that builds worlds. That's electromagnetism. That's what you're touching every time you touch anything. That's the light in your eyes, the fire in your neurons, the bond between every atom in your body. And nobody knows why it exists. But isn't it magnificent that it does?